Hey, AP Stats, we are starting chapter 11 today, and there's only 12 chapters, man. We are getting close, guys. We're going to finish on time. This is all worked out. Don't stop now. You're almost to the finish line. You know what I mean? Okay, chapter 11, Test for Goodness of Fit, is what we're going to talk about today. I want you guys to understand that we are now going to do a chapter on categorical data. There will not be a single X bar in this chapter. Okay, we are counting the number of yeses that go in categories. So we'll be using proportions. This is all about categorical data. Here's an example. M&Ms. According to Mars Incorporated, the company that makes M&Ms, the following is true, that on average, the new mix of colors for M&Ms candy will contain 13% of brown and red, 14 yellow, 16 green, 20 orange, and 24 blues. That better add up to 100%. So let's count some data and fill in the chart. I actually one day went and bought a whole bunch of M&Ms and had one kid just sit in the back and count them all. His name was Albert. He was a funny weirdo that really didn't want to talk to anybody, and so he just had a ball sitting in the back of the corner counting out what colors. I don't know how many he ate. I don't want to know, but we got data, okay? The expected value is something we need. That's what we observed. But for a chi-squared test for goodness of fit, we also need an expected value. Okay, so expected value goes like this. Brown, according to this, there should be 13% of the candies should be brown. Yellow, 14% of them are supposed to be yellow. Red, looking up here, 13% of these are supposed to be red. Orange, 20% of them are supposed to be orange. Green, 16% are supposed to be green. 24% are supposed to be blue. That better add up to 100. But here's how we get the expected value. There's the total number of M&Ms I just found. Multiply that number times 0.13. You get 96.1. Multiply that number times 0.14. You get 103.5. Multiply 739 times 13, you get 96.1 again. 739 times 20%, we should have 147.8. 739 times 16%, we should have 118.2. And 739 times 24, the biggest percent we have is the blue. That should be 177.4. For a total, of course, of 739. And we didn't get those exact numbers. My boy Albert counted out 739 M&Ms in the back of my classroom, and he did not get the numbers that they suggest should be there. So what we could think is that their list of proportions is off. That's what a chi-squared test for goodness of fit is. Did this distribution of percents, does our data fit that distribution that they suggest? That's what this chapter is going to be all about. Do distributions that are suggested fit with the data that we got? So what we're going to calculate is something called chi-squared statistic. Okay, so I want you to go to the left here and put chi-squared there. It's like an X with a little fancy, like that one's like a normal X, but this one's a little fancier. And we call that chi-squared. And here's how it goes. You get a chi-squared statistic, just like we got a Z statistic in the past and a T statistic in the past. Now we're going to have a chi-squared statistic. And it is the sum of all of these terms where I go the observed amount 99 minus the expected amount 96.1 squared and put over the expected number. So I'm just going to write this out on one of them. It would go 99 minus 96.1. That would get squared and it would go over 96.1. You see what I mean? I'm going to write that number underneath. It's 0.0875. For the rest of them, I'm not going to write all of those down. I'm just going to write the actual values. I got 1.76 here, 2.31 here, 0.65 here, 0.716, and the last one is 0.867. Okay, now one thing we can tell when we do the O minus E squared over E to get the chi-squared statistic, these are all terms of what happens when I add them all together. But the different components tell a story. Which one of these is the biggest number? That's the color that was the furthest off from what was suggested. This 111 is nowhere near this 96.1. It's further off than any of the others. See what I mean? So that's going to be an important thing for us later on in the show. Now I'm going to add all these up. And when you add all them up, you get 6.39. You guys, that is our chi-squared statistic. Chi-square equals 6.39. Just like with a z-test, we got a z-statistic equals something. And with a t-test, we got t equals something. Well, now we have a chi-squared test. If we were just interested in blue M&Ms, we would take our sample of size 739, if we were just interested in blue alone. And we'd turn the number of blues that we found, 165, Albert counted 165 of them, we'd turn it into a p-hat, and we would perform a 1 proportion z-test. Didn't really fit on the line the way I wanted. Without the write-up, it would look like this. The probability, the HO is that the proportion of blues is 0.24, like they said. And then we would maybe think that the probability is that it's, we got 165, so maybe we think it's less than. I should put less than 0.24 there. The p-hat we got for blue is 165 over 739, and so that ended up being 0.22. Now, how would I get this z-statistic? This would go p-hat, so 0.22, minus p-naught, so 0.24, over the square root of, I'm reviewing chapter 9 for you right now, the square root of 0.24 times 0.76 over, how many candies do we have? 739 of them. It's a big sample size. So I get a z-statistic of negative 1.27, and that just describes just blue for a 1 proportion z-test. The p-value, I think we've done this enough, I'm going to skip it, so I'm going to go normal, CDF, negative 100, up to negative 1.27 with a 0 and a 1, and I would get 0.1020. So I would fail to reject with a p-value of 0.1020. If I was doing this test for just blue, I would fail to reject the null hypothesis at the level alpha equals 0.05. If I was just talking about blue. You guys are dying to fill those in, I can tell. All right, we'll fill it in. It's the probability that a p-hat would be less than or equal to 0.22 if the null hypothesis was 24. And so that's really the probability that a z, if I took z-scores, would be less than negative 1.27, and that's why I do a normal CDF the way I do. All right, I'm going to get back to this data, though, and we're going to perform a test for this chi-squared statistic. So we're not just interested in blue, we're interested in the entire distribution here. Is this data, where they're all different, is this good enough for us to reject the fact that M&Ms claim that's their numbers? Okay, let's go to page 2. Oops, I got a little angry and I crinkled up my paper there. That's what happens when you teach this long. Okay, now, what we could do if we were insane, we could perform additional tests for each color. Like we could do what we just did on the last page for blue for all 6 colors. That doesn't sound fun to anybody. But that's got 2 downfalls. It's not very efficient. Don't nobody want to sit there and write out 6 tests. But more importantly, it doesn't describe how the entire sample that Albert sat in the back of my classroom and counted, how much that differs from the suggested population distribution. We're talking about a bunch of numbers. I don't want to do 6 different tests that are all individual colors. I want to do one test that tests this entire string of percents. Therefore, we need to introduce a new series of significance tests. It is the chi-square tests. And so here, I'll do it again. You start at x like you would normally start at x, but this one's all curvy and funky. And then we put a square. That's the chi-squared test. Okay? Here we go. We're going to learn 3 chi-square tests in this chapter. This chi-square, now, I think it's kind of stupid that I put a square up there and call it square. Maybe that's not right. But anyway, the chi-square test for goodness of fit, somebody will look that up and send me an email if I got it wrong. It will test an observed sample, like the M&Ms that I bought, distribution. I counted a whole bunch of colors for a whole bunch of M&Ms. I didn't, my boy Albert did. To see if it's different from a suggested, spelled that word wrong, from a suggested population distribution. Can we call the M&M people liars? That's the question. Okay, there will definitely be conditions. That should seem kind of familiar to you. There will definitely be a write-up. That should seem familiar to you. And we will find the chi-square statistic, just like we did on the first page. We add up a bunch of terms. It goes like this every time. Chi-squared is equal to the sum of all of the O minus E over E squared. Oops, that's not right. It's the top is squared, not the whole thing. Ooh, sorry about that. Took a look at it, realized how bad that was. That's why I made this box so big, so I could write it twice. O minus E squared over E. Sorry about that. I'm stupid. Okay, so add up all of the O minus E squared over E. So look, on this first page, I had all the observed numbers that Albert counted. I had all the expected values that I just took the total times these percentages. So for each one of these, like this one, this 2.31, here's how I got it. 111 minus 96.1, square it, and then divide it by 96.1. You get 2.31, right? Then what you do after you find all of these chi-squared terms, you add them up. That's how you get the chi-squared statistic. Okay? All right, so let's talk about a little more notation and variables and stuff, where O in this formula stands for the number observed for each of the different categories. Out of the big sample size N, and for us that was 739, it's the whole sample. E stands for the expected number, which we get by taking that total times each percentage, out of size N for each category. Once again, we will use N minus 1 as degrees of freedom, where N is not 739, N is the number of categories. Okay, so for us, this last one, degrees of freedom would equal 6 minus 1, or 5. It's not 739 minus 1. See what I mean? Okay, this is how we write this thing up. The null hypothesis is a string of percentages. The proportion of brown is 0.13. The proportion of yellow is 0.14. The proportion of red is 0.13. Orange is 0.13. Green is 0.16. And blue is 0.24. A cheap, easy way to write this out, instead of writing all those, is to say the null hypothesis is the proportions suggested in the problem are all correct. You could just write that as a sentence also. But I like to see the numbers, if I'm being honest. And the alternate hypothesis is at least one proportion differs. I don't care how many. If at least one of those is wrong, the whole distribution is off, and they're liars. They lied to me. The chi-squared statistic that we found on the other page was 6.39. The degrees of freedom is 5, because the number of categories minus 1 is 5. Here you go. You ready for the p-value? It goes like this. It's a chi-square CDF, just like you did a normal CDF and a T-CDF. And it goes 6.39 up to 100, degrees of freedom 5. You put it in the calculator just like that. Let me show you what it looks like. I hit second and variables. I go right past the normal CDF. I go past the inverse norm, the inverse T, the T-CDF. We've used all those. There it is, number 8, a chi-squared CDF. The lower number is 6.39. The upper number is an arbitrarily large number. I'll put in 100, and degrees of freedom is 5. My calculator tells me that my p-value is 0.27. Interpretation. If the null hypothesis suggested proportion distribution is true, the probability of observing a result at least as extreme as the one Albert observed when he counted all those M&Ms is 0.27. And 0.27 is way bigger than 0.05. And so we would fail to reject the M&M suggested distribution. That may actually be true. Okay, let's go do one more page here. And that'll be it for today. Look at this big giant homework assignment for you guys. I got 4 problems for you to do. Okay, some more just kind of language here, I think. Each term or component of the chi-squared statistic is a measure of the distance of the observed count from its expected count. So like I said, under each category, all of these O minus E squared divided by E, that's what we're talking about. Each one of those is a term because I add them all together, right? That's what we call those terms. It's a measure of the distance of how far the observed and the expected values are different. The terms are all positive because I square stuff. Okay, I'm counting, so they're all going to be positive numbers here. They're counts. And then when I subtract them, they could become negative, but I square them. So it's always going to be positive. And they contribute to the overall statistic. The chi-squared statistic, you know. So this chapter will also follow up an actual test where we reject or fail to reject with an analysis. Doesn't have to be a big deal. Don't sweat it. Of which component or components were the largest contributor to rejecting. So if we do end up rejecting, we should go look at which one was the furthest off so we could maybe make a suggestion of why the distribution is off, right? So here's where we are. I got to check your understanding for page 681. This is for M&Ms, but it's with peanuts in them, right? And then the suggestion is these are a little different. It goes 0.12, 0.15, 0.12. Orange is 0.23. Green is 0.15 and blue is 0.23. I hope that's what it is. I didn't actually check. I just started writing stuff down. Maybe I should look at the book. Hang on. I keep forgetting sometimes that it's a new edition and it may not be the same because I didn't teach this stuff out of the book last year. Pandemic, you know what I mean? Okay. 681. I'm looking at a check your understanding on 681. Okay, there's no check your understanding on page 681. That's kind of funny. That's in chapter 10. So let's fix that. I am so good at my job. It's just amazing. I just amaze myself. Okay, so talk amongst yourselves while I find what I'm actually trying to do here. I have a check your understanding. Nope, that's the one we already did. Well, hey, it looks like we may just skip this check your understanding. It was silly anyways. It's just silly. We already did the one that we wanted to do. I don't think you need to redo one. Let's go to page 722. I'm just taking a look. Yep, that's actually the right page number. That's good. And then why don't you guys just do 1 through 4, where it's just basically, I think they're giving you the chi-squared statistic and the degrees of freedom and asking you for a p-value for a couple of them. And the other one, you actually are going to find the count. So you got an example in there. You got 4 problems to do. No big deal. And we'll move on with this tomorrow. Silly. Just silly. Have yourselves a good day.